breach path busters using graphs and AI to decode cyber threats. From Kathy Vu, Brian Fong, and Aideen Fay. Please give the loudest screams and stuff. Scream.
My name is Kathy Vu, and I'm here from the Azure Red team. I am the engineering manager for the Breach Path Analytics team, which is part of the engineering arm of the Azure Red team. And we're here today to talk to you a little bit about how we do things on the Azure Red team, what we're doing to tackle scale on the Azure Red team. And my teammate Brian is also here to tell you about the red side of the coin. And then Aideen Fay is here from MSRC Threat Hunting to tell you a little bit about the innovations that we're making in the defensive space. So you'll hear the blue perspective on red teaming. So before becoming an engineering manager, I was a breach operator on the Azure Red team for too long, all right? I'm old. And when I tell people, I go and break into services for a living, I get two questions all the time. I get people asking me, how did you do that? How did you break that? How did you find that weird path through all of these resources to get to your target? And how do I stop it from happening to me? Because I don't want you in my stuff. So hopefully we'll shed a little bit of light on how we do things today. So breaching stuff and breaking into services really is just finding a path to someplace, right? We're either trying to find a key, a certificate, we're trying to get to a particular resource or a particular database. And in order to find our way to that very specific place, we would like to have a map, because wandering around lost kind of feels crappy. So let's talk a little bit about maps and important qualities to have in a map. So first, we really want our maps to be accurate and reliable. Accuracy is kind of a given, right? Because it would really suck to drive your car into a harbor, and it would really suck for me to deliver a report that says I accidentally broke into the wrong place. Or even worse, if I say, hey, I accidentally broke a service as a part of my work, right? We don't want to be breaking things unintentionally. And reliability in today's world can sometimes feel like a given because we're so used to this very highly available world. But I hike a lot in national parks, and there's no internet, and if I'm not prepared to download my maps, then I'm just in the middle of a canyon and I have no idea where the hell I am, and that kind of sucks. And it's really important for the map to know about where you're trying to go. Now, again, in today's world, you're kind of taking that for granted, right? Google Maps, Apple Maps, Bing Maps pretty much know about most of the places that you're trying to go. But if you're old enough to remember those map books, where if you don't have the right one, you're not going there. And there are also a lot of subject matter expertise that don't necessarily exist depending on where you're trying to look for your maps. So for example, if you're hiking and you're going up a mountain, a topology map is really useful. Or if you have the same resource, like a house that's being assessed, different people are going to look at it in different ways. You can have technical engineers look at it, geotech engineers, real estate agents, structural engineers. They'll look at the same resource and have very different perspectives on it, and none of them are more right or more wrong. They just have different areas of expertise and different opinions that we should really take into account. And then we really would like the map to help us to get there efficiently, right? And that can be in the form of, hey, I would really like to avoid tolls on the bridge, or avoid some detections that we know exist in the environment. Or it could come in the form of trying to get there using the least number of hops, or maybe to get to the resource that will get me the most number of stuff at the end of the day. So we're going to talk a little bit about our map, the map that we have built for our internal usage. So our map has a bunch of data in it, and one of the things that we have is access. Access can be something like this, where we have a group and a bunch of accounts that belong to that group, and then the permissions that those accounts have to particular apps or service principals. And then we also map resources, because it's kind of nice to know how the world is structured around us. So things like subscriptions and resource groups and the key vaults that exist inside of those groups. Because if you work with Azure at all, you know that key vaults are awesome. We really like those. And then we also need to see things that are not necessarily your Azure resources themselves, but it's in the periphery and it's totally necessary to run those services. That's things like ADO projects, ADO repos, and permissions in those repos. Because all of these things combine together to make a single story. So I'm going to tell you a little story. It's not a real story, but you might remember it or have encountered it in the past. So once upon a time, we have an engineer who has created a certificate for their app, right? This is necessary because you're working on this app that's going to be released in production, and you kind of need to authenticate to it to do stuff, right? And so in doing the right thing, this engineer puts the certificate into a secret in a key vault. And the key vault, of course, belongs in a resource group, in a subscription, because we're using Azure. And then this subscription, even though the app is a production app, because this engineer is just doing some development and really the MFA stuff is really kind of complicated and I don't want to have to use my phone to auth every time I do my production work. So just for development purposes, we're going to stick it into our pre-production development environment. And then time goes by and we ship our service and it goes to production, and then all of a sudden your day and this engineer's day is just filled with KPIs and OKRs and reliability metrics and all this other stuff. And they completely forget that the app is sitting in production, and they just kind of forget about the certificate sitting in the pre-prod environment, right? Would never happen in real life, I know. So one day, a wild Kathy appears and realizes, either through manual reconnaissance of the service or through this tooling that we've created, and is able to gain access to this pre-prod environment, because this pre-prod environment is likely to have much weaker security policies than the production environment. And then we can move through all of these nodes that you see and eventually get to the production environment. And in this picture here, this is just one single traversal, but you can imagine that if this AAD app has permissions on the subscription to say enumerate more key vaults, we can replay the second half, or right, starting from the key vault all over again, and go steal even more subscriptions and so on and so forth. And so this entire chain of attack is what we consider a TTP. It stands for Tactics, Techniques, and Procedures. And it basically just says, hey, this is one way we know of for an attacker to move from point A to point B. So Brian's going to talk to you a lot more about TTPs in a second. But all you need to know, and all I want you to get from this picture, is that it can take a lot of steps for an attacker to go from one place to another place, right? It traverses through a lot of nodes, and it can be very difficult, even when you own the resources, to audit all of the permissions, especially if you have thousands of nodes to look at, thousands of subscriptions to look at. So we own this service, and we've heard that story before. So I want to talk a little bit about the graph that we've built. It was built by the Azure Red Team circa 2015, 2016, something like that. Our origin story is kind of a mystery because it was built by some breach operators to go pwn a service. And then, we built a lot of tooling. Sometimes they don't persist, but in this case, it did. The next op, somebody else thought, hey, this is cool, and we added a little bit to it, and we added a little bit to it. So since 2015, I think we've rebuilt this thing like 4 times. Each time it's because, oh no, we have a bajillion more nodes that we need to support, or oh wow, we need this to be up like every time we do, every time we want to run an op. So in its current form, there are 265 million nodes. about 485,000 million relationships. And it's, aside from pretty much every single member of the Azure Red Team ever contributing to this, we also have contributors across Microsoft, from M365, identity, MSRC, gaming and devices, because of that subject matter expertise. Right? The Azure Red Team knows how to compromise, one particular technique, but our defenders know a lot more than us in a lot of these subject areas. So traditionally, this is what we used the graph for. We really have breach operators interfacing with the graph and looking at it for breach paths, adding to it when we find that there's missing nodes and missing data, and then we take that and we attack a service. And so, let's recap real quick, right? With this map, we can now quickly find where the important stuff is, because I can enumerate resources and see, hey, there's a key vault that would be nice to steal that has permissions to really good things. And then we can ask the graph, hey, find me a path to this, and use it and send somebody to go get the stuff and steal something from there worth stealing. And that's all great, but there's a problem, right? It doesn't scale. There are only so many people on the Azure Red Team. There's only so many humans, period. And we simply do not have the scale necessary to cover all of Microsoft services. In fact, for every single breach operator in the company, there are thousands of services that need to be covered. So we need to provide Red Team assessments at scale. We need to be able to provide coverage to all of these services in a way that is going to be accurate, going to be comprehensive, and we want to be able to do it in a manner that reflects the most current threat landscape, which is very complex and grows every single day. So now this picture is evolving, and we're going to have some new nodes in this structure here, right? We still have our breach operators who are still interfacing with the graph, who are still pulling new breach paths from there and going to pwn services, and we still deliver readouts just as we always have. But now we have my team, and we're really focused on taking these breach paths, taking these TTPs, and scaling it out across the entire fleet of Microsoft's internal services. And we work with the breach operators to do that. We grab their new techniques that they've developed, and we try to scan for that across all of Microsoft. And then we also work with our blue teams, not only to obviously notify them that, hey, there's this new terrible thing that we have found, please go and help me make it go away. We also work with them to get new data, right? New data points that we didn't even know was an issue, or a configuration that they see in the wild that we don't necessarily keep track of because we're sort of laser focused on breaching stuff internally. And then we take all of that and try to distill it into a format that can be consumed by our service teams and by the people who can actually interact with all of this stuff and the owners of the resources, so that they can go and close down their issues. And so with that, I'm going to hand this over to Brian, and he's going to talk to you about how we're doing scaling.
Hi, everyone. So I'm Brian. I'm one of the engineers working on breach path analytics. And pretty much breach path analytics, or as I'm going to abbreviate to BPA, that's what we use to scale out what we find. It's what we use to take common attack vectors that we see, combine it together, and actually get a better sense of what are the possibilities that exist. So when it comes to BPA, there's actually 4 major components. There is this pattern graph generation. And this graph is going to be different than what Kathy was talking about, that internal security graph or that map of everything in Microsoft. That's going to be different from what we're talking about here. And then we take that result from the graph, and then we do some optimized scanning back on the map. So it gets a little bit confusing. And then the results that we get back are going to be breach paths. And there's sometimes going to be a lot of those, and we want to be able to prioritize it. We want to be able to make effective use of triaging those issues. And then we want to be able to provide clear and concise steps for the service owners to fix these issues. So when we talk about the pattern graph generation, what we do is we take different types of TTPs or attack vectors that we see, and we turn it into a graph. So Kathy showed before an example of what one of those would look like. This would be another example. And pretty much at this step, what we're doing is we're taking common trends that we see, turning it into nodes and relationships. And the idea here usually is that the attacker starts off from the left side and they want to end up on the right side. Things on the left side is usually easily accessible, and then the things on the right side are the things that we want to protect. So when it's just one attack vector, one TTP, sometimes it's pretty boring, and we want to add a few different ones. As we start adding TTPs, they'll be in different colors. Each one that shares multiple colors, so like secrets, for example, has 3 different colors. That means that it's a part of 3 different TTPs or attack vectors. What we have here now is that breach pattern graph, where we could actually start traversing through it and seeing the steps that an attacker would take, what TTPs they may or may not use, and how that comes together. So when we will look at it, this graph can actually be reused for different types of breach path. This could be a way that it can traverse between environments, like non-production to production. They can traverse between services. They can traverse between organizations, or any sort of ways. It's sort of agnostic to the type of breach path that we look at. And so right here, if we want to look at it, we can take the bottom red node to the bottom green node as our endpoints, and we can see like how many different ways can an attacker actually traverse through that. So there's the red-green node is one way. There is the app and key vault, using a part of another TTP actually to traverse through that. And then you can actually go through the apps and secrets. When we look at this full graph, though, how many paths are there from the source to the sink? And so the source nodes are nodes that are on the far left for everybody. In the red nodes, and the sink nodes are the ones that are the green nodes. And those are typically, the red nodes might be things that are exposed to the internet, things that are not super secure, things that are in development. And the green nodes are critical services, critical resources, things that we don't want anyone really touching at all. So we can traverse through the top, through the VM, to the top beige gray node. And then the exact same path exists actually from the red node too. And as we start enumerating through these, with just the 4 TTPs that we started with, or the 4 attack vectors, we end up with 7 different paths. And this is something that you could try to like combine it through manually, but it's a lot easier when you throw it in a graph and you just run a graph traversal algorithm. So what do we do with those results? Well, we take every single path that we get and we translate it into a query that we can then run on the map that Kathy was talking about. Because if we just want to look for every single path that exists arbitrarily, it just blows up. It takes too long, it might take days, and we still don't get our results back. But when we know what type of nodes are at play, when we know what types of relationships are at play, we can then optimize that query, and it runs down into like a few minutes, maybe even seconds to get back thousands, millions of results. There are some things that we actually do that is like we break apart the graph or the queries that we get again just so it runs a little bit faster, because sometimes there's a many-to-one, there's a bottleneck that usually happens. And you get a lot of different ways to get to that node, and you got a lot of different things that are in this peripheral. So we sort of want to shard that up, and that makes our scanning a lot quicker. And once again, these patterns can be reused for different scenarios. From that example that we had, there were 4 different attack vectors that yielded 7 breach patterns, which we transformed into 7 different queries. If we want to look at different types of breach path, we can look at things that goes between organizations, between services, or between environments. Then we sort of inject those values into the queries, and now we have 21 different queries that we want to execute. As we start scaling up, as we start finding more attack vectors, more TTPs, as we start trying to protect different services that come into play, this number grows really, really quickly. And when we talk about the pattern that we're actually looking at, or this pattern graph, it doesn't have to be from the source to the sink. What's interesting is sometimes there are TTPs that goes from one VM to another VM, one subscription to another subscription. And what you can do is you can reuse the exact same graph once you get to that subscription and be like, oh, I can go from this non-production to this production service, and then from this production service, I can actually go to this other production service. And so you can start reapplying this graph. This can also be used for attackers and defenders in the case of, well, I came across this application. Where can I go from here? Or I have this box that I need to protect. How are different ways that people can come into it? With our current service, where we're at right now is we have 7 attack vectors, 7 TTPs. That's still a growing list. It yields 24 patterns. We're focusing on 5 different breach path types, and that means there's 120 different queries that we're running. What we're trying to move towards right now is we're moving away from saying I want to look for this specific breach path or this specific vulnerability, and telling the systems these are things that you need to be aware of. These are the puzzle pieces that attackers commonly use. I want you to put it together, figure everything out, and then tell me what my issues are. So we're moving away from what are we actually scanning for to how do we scan for this. Finally, when you start having a lot of scanning, there's going to be a lot of results. Hopefully not too much, but sometimes the reality is there could be quite a lot of things that we find. And it's going to be expensive to fixing all of these issues. Ideally, we want to fix it all right away. The reality is there's only so many people that we have that can be put onto this issue. So what we want to do is want to fix the worst ones first. We look at all the breach paths that we have, and because we have that map, we know the impact of every single breach path. We know what's in the blast radius. We can even go further hops and be like, how far can this go? And we can start assessing like, which ones do we need to fix first? And some criteria may be like, well, this breach path only has 10 subscriptions in it. This breach path has 10,000 subscriptions in it. Maybe it's better to fix the one with 10,000 in it. Or this breach path over here goes into this developer's box that has nothing and no access, versus these are going into our critical services that house all our database and customer information. We should fix that first. So being able to know the security context of each vulnerability in the chain together gives a lot more incentive for people to fix it, drives a lot more, when we make our decisions, is data-driven. Finally, we also want to look at the left side of the breach path, saying how easy can this be exploited, whether it's exposed to the internet or not. And then those also increase our scores, whether we want to burn down on those first or not. Finally, the last part is when it comes to the remediation step. Some of these breach paths gets pretty complicated. There's a chain of multiple TTPs that cause it to happen. And we sort of want to identify what are some one-step actions that you can do to break this path. What we do now is we have the information of what TTPs are used. We have the information of what resources are being affected. And we can build together a ticket from that to be like, these are all the things that are affected right now. These are where you need to go and what you need to do to be able to break this path. And this is why it's bad, because you're sort of exposing a lot of data that we shouldn't be exposing right now. And this is important because sometimes, at least in my experience, when I'm fixing tickets, if they don't tell me exactly what to do, I get really frustrated. There's a meme that I saw where the husband was about to go to the store and the wife tells the husband, like, go buy a carton of milk, and then if you see eggs, buy 6. And he comes back with 6 cartons of milk. That's my experience sometimes when I'm fixing tickets, is that if it's not clear, I don't know what I'm doing, I could be doing the wrong thing and it's wasting everybody's time. So when we want to come together and look at the whole picture, we have this complicated graph database, this map of everything in Microsoft. And then BPA runs to extract data from that, extract the breach paths that are severe, that are maybe not as severe, but extracts everything. And then we want to be able to provide a one-step solution for people to take. Whether it's something earlier in the path, later in the path, that's up to them to decide, but we want to make it clear and concise. When it comes to scaling this out, we have the graph database, and we sort of want to keep the data fresh and rebuilding it every day. We find many different breach paths that are varying scales of severity. And then we want to prioritize that. And then when we give it to the service owners, we don't want to give them all 10,000 at once. We want to be like, this is the first thing you need to fix. This is why you need to fix it. And when they fix it, then we can start working on the second thing. And this is why you need to fix it. And then as we go through this, they're not wasting their time being like, or sometimes they just don't even start it just because you see 1,000 items, that's too overwhelming. No one wants to do it. But you see one item, it's not too bad. And that's sort of our step and approach to start to scaling this out and burning it down. So to recap, breach path analytics sort of starts off building a different type of graph, an attack vector or breach pattern graph. We want to be able to use those results to scan our map, our internal security graph, in an optimized manner. We take those results, analyze it, grade it, give it to the service owner, the most severe ones, and we want to do it in a clear and concise manner. And now Aideen is going to talk more about what the defenders do with our data.
Cool, thanks, Brian. So yeah, I'm going to talk to you about how my team, MSRC Threat Hunting, collaborated with the Azure Red team to expand their tools and leverage it to unlock stepwise improvements in our defensive capabilities. And I hope in turn that this intuition gives you, well, I hope that in turn this gives you an intuition as to why existing defensive models don't scale beyond small on-premise infrastructure, and how attacker tooling can help you more effectively scale your defensive operations. And of course, the infamous question of, but is it web scale? So as was mentioned before, I'm from the MSRC threat hunting team, and for my team at least, APTs are the monsters under our beds, and our goal is to ruin their fun. So my team's goal is to proactively identify adversaries in Microsoft's infrastructure and the critical security gaps that allow them to operate undetected in the first place. And the great thing about Microsoft is that we have our own in-house APT, the Azure Red team over here that you've gotten to know over the past like 20 minutes or so. And yeah, don't trust their smiles because they are brutally good at what they do. And like one of the reasons why they're so great is that they really humanize the often abstract problem of cybersecurity by delivering attack scenarios right to our front door, and in ways that are very enlightening for the security teams involved and service teams. And after doing several red team ops and purple team ops with the red team, like my main question was like, how are they so effective at what they do? So let's unpack that a little bit. So like one of the obvious cases for this is that as defenders, we're dealing with a completely different problem. We're constantly needing to balance proactive defense with reactive response. And on the proactive defense side, we're basically doing things to make sure we don't get breached in the first place. So that involves doing things like implementing zero trust, enforcing least privilege, and ensuring that our secure development pipelines are robust and secure, and all that good stuff. And on the reactive response side, we need to do things to make sure that when we are compromised or there's an attacker in our network, that we can identify them, we can track them, and ultimately remove them. And that involves investing in our like DFIR tooling, our instrumenting our stuff with observability, and also working on our containment and eviction protocols. But the interesting thing here is that investing in either one of these toolings, so for example, investing in our response tooling, doesn't necessarily support the proactive defense side of the house. Like they're quite orthogonal to one another. So like, what are you going to do? And for small, like if you're working with tens of servers, like yeah, sure, maybe you can do both. Like maybe you can invest in your proactive defense and the reactive response. But once the size and scale and complexity of your infrastructure starts to grow, like you need to start making some difficult decisions about where you invest your time. And this is where attackers have a disproportionate advantage. So as Kathy previously described, like most of the security space can be modeled as nodes, which would be like your services, virtual machines, and user accounts, as well as edges, which would be the relationships between those nodes. And on the defender side, most of the time we're dealing with lists. So we basically work through the list of nodes, and we do this because like the amount of work required to do that scales linearly with the size of your platforms. And there's some interesting like scaling dynamics there where I won't get into here. But on the attacker side, like they don't care about that. Basically, their search space is limited from the number of relationships from their starting point. So they will start from a node and say, okay, where can I go from here, or how can I get to this other node? So like that drastically reduces their search space. It makes it possible for them to kind of deal in graphs. And like defenders can do this as well, but it quickly turns into a like combinatorial explosion of options, because we need to, if we're still needing to enumerate through virtual machines and like enumerate through the nodes, we're needing to search every subgraph. And this quickly becomes very hard to do by hand. And so we tend to revert back to dealing with lists because it's like simpler computationally. Yeah, so this means that like our tooling supports what we need to do, which is generally working through lists, while attacker tooling supports what they need to do and what they do well. So stuff like StormSpotter and Bloodhound here. But like, what happens if you let defenders play with attacker tools? So our team like started to do this. We started playing with the graph database that the red team spoke to you about earlier, and we quickly realized two things. So the first is that it is very powerful. So we can quickly ask complex questions about our infrastructure and get good information about that. But we also learned that it's quite difficult to use, and because we had to learn a new query language, and the interface for actually executing those queries against the database was not very friendly. So we decided to make that easier for defenders to use. So we did this by building a programmatic interface to the graph database, by developing a software library that has basically a list of common breach path questions and blast radius analysis questions that we commonly ask during our threat hunting and response scenarios. And we also wanted to make it fast to use. So we instrumented, we created different Jupyter notebooks that provided batteries included workflows for, say, automating the recon phase of our threat hunting operations, automating some breach path analysis questions. And this made, increased the, I'd say, baseline duration of just writing queries in general, because we no longer needed to repeatedly handcraft these queries to answer these breach path questions, as well as blast radius analysis questions. All of this was encoded in a single software library that defenders or threat modeling teams and red teamers across the company can use to go and understand what sort of blast radius questions do us security defenders ask, and what sort of breach path patterns is the threat modeling team looking for. So in addition to just increasing the efficiency and effectiveness of our work, it actually helps with training as well, which is great. And we also wanted to democratize access to the graph database by building scripts, applications, and automated notebooks that consume this data in new ways. And we're working to make it easy for other defenders to integrate it into their native applications that they use. So I can just give you some examples of what this allowed us to answer. So the first case would be what does this thing let me compromise? What does this node that we know has been compromised give the attacker access to, and where can they go with that thing that they got access to? So in this case, for argument's sake, let's just say we have a development service principal that has access to a key vault that contains a certificate which can authenticate as a production service principal, and that service principal has access to, let's say, a high-value storage account that contains production data. And say during our investigations or threat hunting, we realize, okay, an attacker has stolen this service principal, what does it give them access to? So our software library allows us to quickly understand what that has access to, as well as what are the critical paths from that thing that they've stolen. And yeah, this is useful during instant response when you know something has been compromised. And then it also helps us understand, okay, given that thing, what are the critical paths and which ones should we prioritize so we can start to get ahead of the attacker. Another example of something that we can answer with this is, how could someone have compromised this thing? So let's say we have another compromised node or entity, and this is what we know. We know that this has been compromised, but we need to figure out how did someone get there? So we can then work backwards to figure out what are the paths that someone can follow to get access to this thing. And this is useful to understand, find the initial access vector and start working on that. But it's also good for when you have some sort of critical asset that you're trying to secure, you can figure out what the paths are to that and start locking down the security there. We can also understand what architectural risk patterns exist within a service. And for threat hunting, this is really useful. So here are some examples of some architectural risk patterns that we can quickly look for, which is development to production environment pivots, service to service pivots, as well as publicly exposed infrastructure. And this is really useful during threat hunting to spot common security patterns, which will enable breach paths. But it also helps us basically proactively identify and remediate these risk patterns with the service teams before attackers can exploit them. And something that's been really useful for our team is using the breach path analytics data that Brian talked to you about to quantify the security risk across Microsoft services, because there's a lot of them, and understand which ones the threat hunting team should invest in. And this helps avoid bias in our defender response and investments. So yeah, this works great. If you have everything set up and you know what you're looking for. But velocity matters at scale, and it can be the difference, and being able to do stuff quickly can be the difference between keeping up with an adversary or them being so far into the distance that it can be quite demoralizing and affects your response. And the software library itself, it requires you to know what you're looking for, because you have a predefined set of functions, and if you want to look for something that's outside of those, it takes a bunch of time to add something new in there, like a new blast radius analysis scenario or breach path scenario. So what we wanted to do was remove this friction that we had gotten feedback from responders. So we wanted to reduce the setup time for getting this set up and someone being able to leverage the power of the graph database. And we also wanted to remove the need for limiting people to predefined questions. And what this led us to, with the help of the Azure Red team, was building a chatbot interface using large language models that allowed defenders input free flow text and basically get responses from their natural language questions. And as you can imagine, this allows us to ask more novel questions and get more interesting responses, because it's a more open-ended environment. We're not limiting ourselves to predefined use cases in our software library. And we did this through just few-shot prompting to generate the queries themselves. And we also added extensible renderers so that defenders can visualize the results that the graph database returns. So this can be in graph format, tables, file exports, and also written summaries of your results using large language models. So now that we've shown you what we've done, I want to leave you with a few thoughts on how can you apply these security patterns to your own infrastructure. So the first thing is that the single machine mindset for solving security problems is not good enough. Individually patching servers isn't the stream of vulnerabilities is just going to keep coming, and individually patching servers, server by server, it's not going to help you get ahead of attackers. You can say the same thing during active response, stopping to drill down and do forensics on a single machine while the attack is proceeding. It's basically, you're always going to be behind from the attacker. So this is why it's important to view your infrastructure as a system and identify the edges and relationships within that system, because that is where the attackers operate. And the second thing is that security is an architectural problem. So think about how you can remove that glue between your systems that attackers move between. And that involves, the layer that you can start solving those problems is through stuff like ephemeral secrets, zero trust, least privilege, and investing in those spaces can remove the leverage that an attacker has when they do compromise your systems, because they will. So yeah, focusing on removing those architectural risks can remove the need for you to invest heavily in the security operations, risk management, stuff that you need to do if you're not removing that architectural risk, because removing that architectural risk increases the overall security baseline of your company. Yeah, so as I mentioned, focus on breaking the graph through architectural changes and make the remaining glue that you can't remove untraversable. And finally, graph tooling is really great for helping you identify these architectural risk patterns across your infrastructure and take steps to proactively remove them so that before the attackers compromise or use those architectural risks against you. And the final thing that I'll say is that I think the main takeaway from this is that thinking as security as a systems problem and using tooling that can help you model and visualize those security risks is what will help you keep pace with an attacker. Cool. Thank you, everyone.